Hello, everyone. In this video, I will be going over problem 6 of chapter 5 in the Fundamentals of Mass and Heat Transfer textbook. In this chapter is all about transient conduction, and this problem specifically has to do with lumped capacitance, characteristic lengths, and BO numbers. So this problem asks us to consider 7 different cases of 6 different shapes in 6 different situations. They ask us to find the characteristic length as well as the BO number, and if lumped capacitance is a reasonable assumption for how to approach these problems. So the first shape is a toroidal shape of diameter d equals 50 millimeters and a cross-sectional area of 5 millimeters squared with a thermal conductivity of 2.3 watts per meter Kelvin and a convection coefficient of 50 watts per meter squared Kelvin. Now, a toroidal shape is pretty much a donut shape. It's just a cylinder wrapped around to become a hoop. And this one, there is no easy way to interpret this shape. Best we can do is use the characteristic equation, which is just volume over surface area. Volume of a torus is 2 pi squared big R little r, with big R being the radius from the center to the center circle inside the torus, with little r being the cross-sectional radius. And the surface area is 4 pi squared r big R little r. So if you just cancel that out, the characteristic length of a torus is simply r over 2, which in this instance is equal to rad 5 over 2 rad pi. So if you plug this all into the BO equation, we get a BO number of 0.433, meaning that lumped capacitance is not a valid assumption for this torus. Next up, we have a bar with a cross-sectional area that is a rectangle. So in order to solve this, you take the volume of the entire bar minus over the 4 surface areas of the 4 side faces, giving us a characteristic length of 0.009 meters. And then when plugged into the BO equation, we get a BO number of 0.0086, meaning that lumped capacitance is valid in this instance. In problem 4, sorry, not problem 4, in case C, we once again have a bar, but this time it has a hollowed out middle section. In this one, I believe that we are able to utilize the commonly accepted plane characteristic length, that being that in a plane, it's just going to be the length, the thickness over 2, the thickness in this case being the the thickness of the sides, surrounding the empty tube, which is just going to be big W minus little w all over 2, which gives us a characteristic length of 0.002 meters or 2 millimeters. Plug that in. Next, we'll have to find the thermal conductivity of aluminum alloy 2024. I forgot to mention this, but uh, we also had to look it up in case B for the hot AICI 304 stainless steel, which I got to be 16.2. But going to MatWeb for aluminum alloy 2024, I found a thermal conductivity of 151 watts per meter. So plug that into the BO number, gives us 0.005, meaning that lumped capacitance is valid for case C. Case D is a long cylindrical bar, meaning that characteristic for BO number calculation is equal to R over 2, which is equal to D over 4, which is equal to 0.013 over 4. Uh, I did not uh, simplify that a bit further down. The Now because for case D, we are given a mass, we need to find the density such that we can actually determine what type of steel this is. So the volume of a cylinder is just pi r squared times the length, or 1/4 pi d squared times the length. Once we have the volume, we divide the mass by said volume, giving us in this instance a density of 8,237.13 kilograms per meter cubed. I Googled this, and it appears that the closest type of steel to this description is 17-4 pH steel. So looking at those material properties, it gave me a thermal conductivity of 18.3 watts per meter Kelvin. So plugging that into the BO equation gives us once again a BO number of 0.005, which is valid to use. Case E is a sphere, meaning that characteristic length is R over 3 or D over 6, which is about 13 millimeters over 6. I'm just verifying that I did, in fact, put in the correct numbers. Yeah. Giving a characteristic length of 0.002167. I don't know what I wrote there, but that, oh, yeah, that is K equals 130, which is the thermal conductivity for the sphere as listed in the problem statement. It has a surrounding temperature of 18 degrees C or 291 Kelvin, and an initial temperature of 373 Kelvin or 100 degrees C. I immediately decided to convert it to Kelvin because we are going to have to deal with radiation in this instance. And there was an emissivity of 0.75. So normally the BO number is HLC over K, or thermal convection coefficient, times characteristic equation over thermal conductivity. However, this is in a vacuum, so there is no convection, but we can equate the radiation of the sphere to a thermal convection coefficient. All that we have to do is, and that equation is simply dH is equal to the emissivity times the Stephen-Boltzmann constant times the initial temperature plus the surrounding temperature times the initial temperature squared plus the T surrounding squared. This is why I converted it to Kelvin, because if I had kept it in Celsius, it would not work. If you using Celsius is fine if it's just addition and there's no powers, but as soon as there are powers, it needs to be in Kelvin, giving an H of 6.31963 watts per meter squared Kelvin. Plugging that into the BO number gives 0.001, which is once again valid to assumed lump capacitance. Now, the final condition, or the final case, is for both case F and G. It describes that a long cylindrical rod of diameter 20 millimeters, a density of 2,300 kilograms per meter cubed, a specific heat of 1750 joules per kilogram Kelvin, a thermal conductivity 16, is suddenly exposed to convection conditions with T infinity is equal to 20 degrees C. The rod is initially at a uniform temperature, T equals 200, and after 225 seconds, it reaches a spatially average temperature of 100 degrees Celsius. So this has a lot going on, and it doesn't give us the convection, and it doesn't give us any details to the air around it to allow us to assume any kind of convection coefficient. So in order to approach this, we actually have to first assume that we're able to use lumped capacitance and then work backwards to be able to verify that it's actually correct. So I've already simplified the equation a bit, but lumped capacitance says that E times the BO number, E to the B negative BO number times the Fourier's number is equal to a final temperature at time T minus the ambient temperature over the initial temperature minus the ambient temperature. So if you just simplify it out, I got it to be in this form. From here, I honestly just put it into my calculator, which has a solve function to give me H. The surface area of this is going to be 2 pi RL or pi DL, and the volume is, once again, pi R squared over L, or 1/4 pi D squared times L. You plug all these defined values into the equation and solve for H, you'll get a convection coefficient of 241.77 watts per meter squared Kelvin, a very high number, but when plugged into the BO number, you get 0.0755, meaning that it is valid to assume the lumped capacitance approach to even find it. However, in condition G, this is very similar to condition F, except the diameter is now 0.2 meters instead of 0.02 meters. Again, just once again, plug it into my old equation, this time getting an H 10 times greater, or 2,417.77 watts per meter squared Kelvin. Plugging that into the BO number, it is now 10 times greater and is greater than 0.1, meaning that it is no longer valid to assume that lump capacitance can work in case G. So that is my explanation and my process for going through problem 6 in chapter 5 of the textbook. I hope that this was helpful, and thank you for watching.